You know by now that given a transfer function g of s, which is equal to s raised to some power n, which is an integer number, its frequency response is given by j omega power n, and consequently the gain of this g of j omega in decibel is equal to 20 times the logarithm of base 10 of this absolute value, j omega power n. We will end with 20 times the logarithm of base 10 of omega power n, which is positive, so we no longer need the absolute value. And since this is a logarithm, we will have 20 times n logarithm of base 10 of omega. As to the phase of gj omega is equal to the phase of j power n omega power n. Now, this is a real number. It does not change the phase. We will just have the phase of j power n. And as we know, the phase of j power n is equal to n times 90 degrees, which is the phase of j, the imaginary unit. Consequently, when we represent this in a Bode diagram, the Bode diagram, remember, has in its x-axis the frequency in a logarithmic scale. So the gain will be like this if n is positive, the slope being 20 n decibel per decade. Logarithm of base 10 of omega is what I have here in the x-axis. The phase, if n is positive, will also be positive and equal to n times 90 degrees. Of course, if n is negative, we will have the same thing, but with a negative slope here, 20 n decibel per decade, and a negative phase here, n times 90 degrees. Consequently, when we have a generic transfer function, which is a rational transfer function in S, that is to say, it is the ratio of two polynomials in S, or in other words, a ratio of two linear combinations of integer powers of S, we can factorize both polynomials, making explicit the zeros and the poles. The zeros and the poles, as we know, are either real or, if complex, appear in pairs of complex conjugates. As we also know, we expect to have more poles than zeros. In other words, we expect to have a transfer function which is strictly proper, since transfer functions which are not strictly proper bring problems of causality. They will have outputs that depend on future inputs. Now, if this happens, then the number of poles being larger than the number of zeros by 1, 2, 3, and so on and so forth will determine how the frequency behavior of G of S is at high frequencies. We will have a Bode diagram that at high frequencies will go down with a certain slope, which is equal to 20 times the number of poles minus the number of zeros. This, of course, in decibel per decade. The phase will be equal to minus 90 degrees times the number of poles minus the number of zeros. This slope, of course, is also negative, just as the phase is negative, because we will have, as I said, in actual plants, the number of poles exceeding the number of zeros. As to low frequencies, if there are zeros or poles at the origin, we will also have here a slope, which will be positive in the gain. If there are zeros at the origin, this corresponds to a positive phase. Or this slope may be negative if there are poles at the origin. This corresponds to a negative phase here. Or else, if there are neither poles nor zeros at the origin, we will have some constant value here, corresponding to the static gain, a value which will be positive if the static gain is larger than 1, and will be negative if it is less than 1. As to the phase, it will be either 0 degrees if the static gain is positive, or minus 180 degrees, or plus 180 degrees, which is the same, if the gain is negative. All this you know. And consequently, if you were shown a Bode diagram of a transfer function like this, you will be able to say what the transfer function is. A system with this gain behavior, with a slope here of minus 20 decibel per decade and a phase here of minus 90 degrees, will be a system which I can describe using a first order transfer function. At low frequencies, I have a constant gain and a phase of 0 degrees. B divided by P for low frequencies will be the frequency response of this plant. This is larger than 1 because 20 times the logarithm of base 10 of B over P is positive. B over P is also positive because this phase is 0 degrees. Here we have a slope of minus 20 decibel per decade. This tells me that there is one pole. Indeed, at high frequencies, when omega becomes very large, this is neglectable. We'll just have B over J omega. This is the behavior of one pole that corresponds to minus 90 degrees. The worst that can happen, of course, is that we may have here some resonance peak, or else we may have here a behavior which is not consonant with only one pole. And in this case, we may need to get our model more complicated by adding zeros and poles. But of course, given this behavior at high frequencies, we will know that at the end, the number of poles will exceed the number of zeros by 1. And given this behavior at low frequencies, there are no poles or zeros at the origin.